It is tensor as a linear transformation. So I am introducing the topic of tensor today, and I am going to show you that a tensor is a linear transformation. And even in this opening page, you can learn some things about linear transformations. For instance, you see this picture where some well-washed sea rocks are piled one on top of the other. Now, I want to ask a question from the class. Can you see that this picture and this picture are exactly the same pictures? The picture lying horizontally and the one that is slightly inclined on this page. Do you agree with me that they're the same picture? Anybody? Does anybody want to? Okay, you can see that these two pictures actually are the same picture. Now, the class again, what is the difference between the two pictures? Even though they are the same picture, but you know they are not exactly the same. What is the difference? Okay, the orientation, then the size, okay? The orientation and size. So there are two things that happened, the orientation and size, okay? Is there any other difference? We have looked at two things, orientation and size. Is there any other difference? Their position, okay? Well, the angle is the same thing as the orientation. One is compressed, it's about the same thing as the size, position on the screen, location, okay? Any other difference? Is that all the differences between the two? Are those the only differences between the two pictures? Okay. You are right. You are, center of gravity. Okay, I agree. You are right. You have already been able to tell me what the differences are. Is there any other way I can change the main picture that you will still recognize that it's the same picture, but I did something? Is there any other thing I can do apart from changing the orientation, the position, and the orientation, the position, and the size? Is there any other thing I can do to this picture? Is there anything I can do? Now, as I am pressing you to answer the question, what is a transformation from a mathematical point of view? That's where we are going. I want you to really have a clear answer to the question, what is a transformation? When Jesus said there's nothing else we can do. Do you all agree with him before I answer the question? If you don't agree with him, tell me what else we can do to this picture. If you agree with him, say you agree. Let me see that. I want to see, okay, Iyano agrees. Who else? Who else wants to try? Admin, please remember to give me a transcript of the chat at the end of the class, okay? Who else agrees? Probably editing the image in terms of color, correction, or something, okay? That is, okay, somebody disagrees that there is all that there are other things we can do. We can do some photo editing. Okay. Okay, suppose we don't want to do some photo editing. We don't want to change color. We don't want to put any new thing. We can change the opacity. We can enlarge it. Okay, which is written as changing the size, enlarging or contracting the same thing. Okay, let me now give you another example of what we can do. Suppose I bring a concave lens or a concave mirror or a convex lens or a convex mirror. You know that I can transform it. I can change the size, but I will let that change of size be position dependent. Do you agree that I can do that to this picture? I can bring a convex lens, and when I give convex lens, it will distort the picture in a particular way. Do you agree? There will be some distortion. So that is another way. That's another transformation. Okay. Now, I want to tell you that other transformation of bringing a convex lens or a concave lens that distorts this is not a linear transformation. But this transformation you are seeing now, where all we did is change the size and reorient it, is a linear transformation. So you are seeing an example of a linear transformation just based on the photograph. So linear transformation is not just an abstract mathematical concept. It's something that you can appreciate. You can see that there is a fundamental difference between a situation where all you have done is you just reorient and contract or expand, compared to when you now started distorting. Once you begin to distort, you are going beyond linearity. If you limit yourself to linear transformation, all you can do for the picture is that you can enlarge or contract or reorient or change its position. If you do any of those things, you are still in the realm of linear transformation. So any change can be called, for want of a better term, a transformation. A transformation is a change. But what you are doing here is that we want to distinguish between when a transformation is linear and when a transformation is not linear. When we are dealing with tensors, you will see that we are going to be dealing with transformation of vectors that are linear. So we have started now by just seeing an example in a picture form, how you can transform something linearly and how you can transform that same thing non-linearly. If you transform linearly, there's no distortion. But if you transform non-linearly, there can be distortion. Even though you didn't change the color, you didn't change any other thing, you didn't add any new elements, but you have distorted. Some stones that look small may look big, and some stones that look big may look small. So once you start doing things like that, you are having non-linearity. Because in this transformation you see here, even if we shrunk the thing, the ones that were bigger here are still the ones that are bigger in the transformed object. The ones that are small are still the ones that are small. The ones, the orientation, the relative orientation of one to the other is maintained. Once you have all that orderliness in the transformed object, you call that kind of thing a linear transformation. You can see how a linear transformation is different from a non-linear transformation. In a linear transformation, there is a regularity. There is a maintenance of relative positions. There's a maintenance of relative sizes. No matter how you transform, as long as you are transforming linearly, there are certain things you can expect. But when you transform non-linearly, it is possible for a small pebble to become bigger than a stone. And the stone now can shrink. By the time you are doing that, when there is no longer any relationship between the original size and the final size, then you are no longer doing linear transformation. And you are not transforming uniformly from one to the other. This is an example. We will go further into deeper mathematical definition of linearity, but this is just to let you see that when we talk of transformation, and we talk of a linear transformation, we are not talking about something esoteric or something so far-fetched. It's something that you are used to, you can see, and you can understand that there is a difference between a linear transformation and a non-linear transformation. There are certain regularities you see when the transformation is linear. Objective of today's lecture: a transformation is a rule, a process or procedure for obtaining an output when an input is supplied. Let us repeat that. A transformation is a particular rule, a process or procedure for obtaining an output when an input is supplied. For instance, in the case of the picture, you take the picture, you redo the size and you orient it. That is all we have done there. So that is the process or procedure for obtaining an output when an input is supplied. So we can transform all the photographs in our album this way, and we have applied a transformation rule. Once the procedure is specifically, explicitly stated, that transformation is defined. If you have not stated the rule or the process or the procedure, you have not yet defined the transformation. So you must define a transformation. A transformation whose rule or procedure or process has not been fully specified or supplied is not yet defined. To know that a tensor must first transform a vector to a vector. So what a tensor is anything, any transformation, any rule, any process, any procedure that if you subject a vector to that procedure, you will obtain another vector. That is the first thing about a tensor. A tensor is a rule. that you can use to transform a vector to another vector. And that vector, the transformation from one vector to the other must be a linear transformation. So if you transform a vector to a vector and the transformation is not linear, what you have done is not a tensor transformation. If you transform a vector to something else, even if you transform it linearly, it is still not a tensor. Two conditions must be satisfied for something to be called a tensor. It must transform a vector to a vector, and it must perform that transformation linearly. Something transforms linearly, and when you supply a vector, it gives you another vector. Then you say that that transformation is a tensor transformation, or the transformation simply that the thing that you have done is you have applied a tensor. So if you can find that thing, you can define that thing that transformed a vector to a vector linearly is what we mean when we talk of tensor. To be able to recognize a tensor transformation and a non-tensor transformation, that is one thing we also will deal with in this class. And to learn to work things out, knowing that they cannot be known just by looking at them. So if I give you a transformation and say, what transformation is this? Say, oh, you don't just open your mouth and answer. You first of all check, what was the input? Was the input a vector? What was the output? Was the output also a vector? How was the transformation performed? Was it performed linearly? Then after you have tested all of that, you now come back and tell me, this thing is a tensor. Or when you find that any of those rules was violated, then you can say, well, this thing is not in tensor. I want you to work things that way, not by just guessing or by quickly talking when you could be quiet. Sometimes we get into trouble when we should keep silent and we are talking. So that is it. So you don't talk until you have worked it out. You've seen whether what was input was a vector, what was output was also a vector, and the transformation that was performed was a linear transformation. On the top right corner here, we are looking at vector transformation. The vector V is a vector transformation because we can operate it on a scalar. If we operate it on a scalar, we just get a scalar, a scaled vector, which is still a scalar, the argument is a scalar, but the result is a vector. If you transform it with another vector using a dot sign, the argument, the W is a vector, but the result of the transformation here is a scalar. Then there's another transformation here, which we call a vector product. What is inputted is a vector, and the output is also a vector. So a vector can transform in all these ways, where the result can be a vector, can be a scalar, can be a vector, can be a tensor. So the first three is clear to you. The last one, I think I mentioned it in the multivariable calculus. I don't know whether you remember that. But you can see that it's not only tensors that can be transformations, even a vector can be a transformation. And it can transform a scalar, it can transform vectors in different ways. But in case of tensor, we are looking at something that transforms a vector linearly to another vector. We will look at that as we are moving on. There are other issues that we are going to look at. We're going to go back to multivariate integral calculus. We've already seen Green's theorem, divergence theorem. We are going to see them now from the point of view of tensor analysis. We're going to see the differentiation of an integral, the Leibniz-Reynolds transport theorem, which we almost touched last time, but that will be a major issue now. And then we are going to do computations and evaluation. We'll use Mathematica to compute theorems and application of these results. I will show that all the results you will see in your MacBook are simple deductions you can do easily by programming. I will gain insight that would have eluded you otherwise. So we're going to go back to multivariate integral calculus after we have learned a little bit more about tensors. Okay, having said that, we now want to ask ourselves, what is a tensor? And the second question is the sun, the same sun, the sun that shines on us every day. Is it a tensor? I'm not going to answer that question. I will expect you to be able to answer that question after 2 or 3 slides. You should be able to answer yes or no, whether the sun is a tensor or not, by our definition. Okay, let us clarify popular usage. The word tensor by a historical accident does not mean tensor in general. Whenever we use that word without any adjective, we are talking about a second order tensor. If I just say tensor and I don't say any other thing, I am referring to a second order tensor. If I want to talk about any other type of tensor, I will tell you the order of the tensor. So if I don't mention the order of a tensor, I am talking about a second order tensor. If you mean any other tensor, you must be specific. Consequently, if I'm talking about a scalar is a zero order tensor. A vector is a first order tensor. And a tensor is a second order tensor, but there are higher order tensors, like there are third order tensors, there are fourth order tensors, there can be any order. But often, most of this lecture, most of the discussion of vector or tensors will be dealing with second order tensor. We will touch we will look at some important third order tensors and some fourth order tensors that will arise. But most of the time, 95% of the time, when we are talking about tensors, we are dealing with the second order tensor. Assumption. We assume you are familiar with scalars and vectors. So we shall be spending our time on second order tensor in the following slides. There are higher order tensors that shall be introduced later. But the question we have not yet answered is the sun a tensor? Now, if we give the sun a vector, okay, I say if we give the sun a vector, how can you give the sun a vector? Okay, I want to see whether you can tell me how can I give the sun a vector? How? How can I give this? I say if you give the sun a vector, how can I do that? Well, since nobody seems to be making progress on that, let me tell you how we can give the sun a vector. Okay, Adewale Busari has tried. To give the sun a vector, this is what we do. You first of all ask, what's a vector? A vector, if we leave ourselves as saying a vector has magnitude and direction. So if I decide to use a stick to represent the length of a stick to represent the magnitude of the vector, and the orientation of the stick to represent the direction of the vector. So I can bring the vector, I can bring that stick, which gives me the magnitude and direction, and bring it out to the sun. Then I've given the sun a vector. The sun can now begin to, the sun can now be allowed to cast a shadow, in which case it is transforming that stick. If it transforms that stick, if I get something that has magnitude and direction, then I have another vector. So the only thing remaining is that transformation linear or not? So we all agree that we can give the sun a vector? Do we agree now that we can give the sun a vector? Because if we take a vector as something that has magnitude and direction, do we agree that if we allow the sun to create a shadow of that thing, that shadow also has magnitude and direction, and therefore it is a vector? So if we give the sun a vector and we decide we look at a particular plane, the sun will reflect by shadow. We cast a shadow on that plane, and that's another vector. Now the next thing is that transformation linear? That is the big question. And let us go back to this as we are going on the way to check whether what the sun does is actually linear or not. Look at, you see the arrows in blue, the vectors in blue are of the same size. The vectors in, what is this color now? I don't know, I'm colorblind. I can't call this orange. I don't know. What is it color? You can see that this is yellow, but we don't know what this color is. Okay, you can see another vector lying on the plane. So the shadow and the vector are the same. So the vector is behaving like an identity tensor here because it doesn't change. There's no difference between the input and output. You can see that this blue one, the vectors that we get from the sun are essentially the same. Because when we put the same thing, when we put the same vector, we get the same transformation. So if this vector is equal to this vector, the transformation of this vector will also equal to the transformation of this vector. If this vector is bigger than this vector, the transformation of this vector is also bigger than the transformation of this vector. If we have a situation where three vectors are stacked, then the transformation of the three vectors are also proportional to the original vector. In this case, you can see that all these things are showing that the sun transforms linearly. The sun transforms linearly, and therefore is actually a tensor. Okay, I have two things on the. Okay, pink. Thank you, Ibinijesu and Chioma. You have helped the colorblind man to know color. I don't know color. Okay, so you can see why I deliberately made the sizes and colors the same. So the ones that are the same color are the same size, and you can see what do you call it now? They are reflections from the sun. They are shadows actually from the sun. So they are shadows from the sun can be seen. So I can say that the sun is a tensor in the sense that if you supply a vector by magnitude and direction and you give it a particular plane, if you change the plane, the same thing, even though the sizes of the shadows may be different, but the same idea that the longer one will produce a longer shadow, the shorter one will produce a shorter shadow, and as long as you are doing it at the same time. So, and if you have a sum of three vectors, the shadow is also the sum of three shadows. So if you have this blue and yellow and pink, if you put them all on top of one another and you add their shadows, it is the same as adding the shadows of the individual ones together, you get the same result. So the transformation of a sum is sum of the transformations. The transformation of a weighted sum is the weighted sum of the transformation. The transformation of it. So when all those things are satisfied, you have a linear transformation. And the sun is an example of something that can produce a linear transformation of a vector to a vector. Therefore, the sun is a tensor. So if we give the sun a vector, can we make it another? Can it make another vector in response? The answer is yes. Until you are supplied with the rule, the tensor is not defined. You can see that we have to supply the rule. Okay, how do you give the sun a vector? We have to explain. How do we give the sun a vector? We have to explain that you have to create a plane. Because if the same sun is casting a shadow on a sphere, if the same sun is casting a shadow on a sphere, will that be a linear transformation? Let me see what your answers are. Will that transformation be linear? If instead of a plane, if the sun is casting its shadow on a sphere, the transformation will not be linear. So the transformation we are saying is when the sun is supplied with the vector and the shadow is being cast on a plane surface. So that is the only time. If it is being cast on a sphere or on a non-planar surface, then it is no longer a linear transformation. Even if it is still a transformation of a vector to another vector, the transformation is no longer linear. A tensor is a linear transformation of a vector that produces another vector. So a tensor is a linear transformation of a vector that produces another vector. Mathematically, if you want to say what I've just said now, we want to say it mathematically. We are not saying anything else, but we are saying it in a very symbolic and parsimonious form, which a mathematician will use. We will say, given U and V are members of the Euclidean vector space. That's what this means. The transformation T, which is a tensor and is a member of the linear space, with operand u, which is a member of the vector space, gives the output v, and we can say v is equal to tu. This is one way to express the transformation, and this equality is to remind us that the result of that transformation is a vector which we call v. You let t operate on u, and you get v. Before I move on, let me tell you that this statement here is not universal. There are authors and textbooks that you will read which will put a particular sign between this t and u to express the transformation. It can be a dot, it can be a circle times, it can be anything other than just leaving it blank. But we would, for our own purposes, we would just put the vector, the tensor, and just concatenate it with the vector and represent the transformation that way. And we say that the result of that transformation is another vector v. So that is why you say v is equal to tu, that is t operating on u. So when you see tu, read it as t operating on u or t transforming u. It is not t multiplied by u, because you don't have multiplication in your elementary notion of scalar multiplication. Is not applicable here. We are talking about a transformation. This is just the way we write it. This is the way we write it. For instance, t here can be the sun, and u here can be any of the vectors we saw before, and v is the result of the shadow. So if we look at this now, this is u, this blue vector is u. The t is the sun shining on it and creating this shadow, and this is now v. This shadow here is v. So do not read the meaning of multiplication into this. It doesn't tell you about multiplication. It's just a simplistic way of expressing t transforms u to v. So when you see this, just say t transforms u to v. Sun creates a shadow v out of the vector u. If you read it that way, you will not be making some simple mistakes that beginners make. Don't read multiplication into it, because these are bigger objects, and multiplication in your elementary notion of multiplication may not be applicable. So if that transformation is linear, then we say t is a tensor, because it's transforming one vector to another vector. And if it does that linearly, we say t is a vector, it's a tensor. It's a tensor if the transformation is linear. It is the transformation from one Euclidean vector space to another. Depicting the set of tensors as L, we can also write it this way, that the set of tensors is such that it picks something from the Euclidean vector space and creates another member of the Euclidean vector space. So it is transforming from the Euclidean vector space E to E, because U is a member of this space, and V, which is the transformed something, is also a member of this space. So it takes something, it takes a member of the Euclidean vector space, and it produces another member of that Euclidean vector space in a linear way. When it does that, we say it's a linear transformation. So all of these are expressing all the things we have been talking about since the beginning. This is how a mathematician will write it down. And when he writes it like this, it means nothing different from what we have been saying. It's just the way he remembers it and the way he likes to write it. And if we write like that, we would find out that we have a very compact way of writing things. But do not let that fool you into now misinterpreting what you have seen. The interpretation doesn't change. It is the way it is written that has changed. So this page 12 here is the definition of a tensor. And anytime we have problem with any tensor, we are coming back here. We are coming back here to perform all the tests to say, okay, did the thing transform a vector? And when it finished transforming the vector, did we get a vector? If the answer is yes, was the transformation linear? If the answer is yes, okay. The thing we are looking at is a Adewale Busari, please stop raising your hand. Just go to the chat room and make a comment. So please, class, I don't permit raising of hands in this thing, because there may be other lecturers in the session that can answer your question while the class is going on without my stopping. And it is also possible when you post your question that another student can see it and answer you without interrupting me. And there will be a record of that question that if it is not dealt with through the lecture, I will find a way of introducing it in the next lecture and find a way of letting you have the answer. So it's more effective to place a question on the chat room than to just raise a hand. So I'm waiting for you to just type your question in the chat room. I keep checking that chat room periodically. So linear transformations. Okay, I'm sure the linear transformation of a shadow is now beginning to be clearer that it is a tensor transformation. In the figure here, let the brown arrow labeled X represent a vector line on the ground. Assume the other arrows are vectors casting familiar shadows on the ground. Examine the relationship between these vectors and their shadows. We use the word transformation to represent the relationship between the input vector and the output vector. So whenever we talk of transformation, we are talking of how this shadow came from this object. How the shadow that is exactly the same thing as this object came from it. Then how these three shadows came from these three objects. How this single shadow came from this single object, and so on. The word transformation, that is what we mean by transformation. When you use the word transformation, we are talking of how these things came from here, how this one came from here, and so on. We don't have any other meaning. So just know that that is all that the word transformation means. It doesn't mean anything more than that. So questions. Question 1. What determines the size or magnitude of each shadow? In a tensor transformation, what determines the output? If two vectors are equal, what can you say about their shadows? If they are opposite, what can you say about their shadows? If one vector is twice another, will the shadow be twice the shadow of the other one? If we add two vectors, what is the relationship between the resultant shadow, their individual shadows, and the vectors that make up the shadow? Those are the questions to ask when you want to know whether what you are dealing with is a tensor transformation or not. Adewale Busari, your questions, if first order tensor result in scalars, do they still satisfy the transformation, the definition of tensors? You have misunderstood me. I said whenever you use the word tensor without any adjective, you are talking about a second order tensor. So all we have been saying so far, we are talking about second order tensor. We are not talking about vector, we are not talking about scalar. So we are saying that the sum is a second order tensor. Whenever I use the word tensor without qualifying it, I am referring to a second order tensor. I'm not referring to a vector, I'm not referring to a scalar, and I'm not referring to triad or tetrad or higher order tensors. I'm only talking about this class is essentially discussing second order tensors only, and nothing but second order tensors. Busari, is that clear? If it is clear, fine. I think at this point, I want to pause for a break. It is 10 to noon now. I will give you a 20 minutes break to ponder what we have been discussing and then be ready 10 minutes past noon. Thank you very much.